Hi, everybody. Now let's look at two applications of Lagrange's theorem to problems in number theory. Um, these are called Fermat's and Euler's theorem, but they're really special cases of Lagrange's theorem. And they're surprisingly useful in practice. And if we have time, we'll discuss a little bit about how they play a role in cryptography. But for now, let's just look and see what these two results say. So before we can state the results, we need a little bit of preliminary work because both Euler's and Fermat's theorems are statements about the group U of n, which is the multiplicative group of residue classes mod n, which have no factor in common with n. And just to remind you, so for example, the group U of 7 consists of the elements 1, 2, 3, 4, 5, and 6. It's the residue classes mod 7, omitting 0, because 0 has a factor in common with 7, and the group operation is multiplication. Mod 7. So U of 7 is a group. It has 6 elements. What about U of 15? Well, U of 15 consists of the residue classes that have no factor in common with 15. So in other words, it's the residue classes that are neither divisible by 3 nor 5. And let's work out what those are. And one way to do that is to write down all the residue classes mod 15. Zero up to 14, and cross off the ones which do have a factor in common with 15. So 0 does. Basically anything which is divisible by 3 or 5, we want to cross off. So 3, 5, 6 is divisible by 3, 9 is divisible by 3, 10 is divisible by 5, 12 is divisible by 3, and I think that's all of them. So U of 15 consists of 1, 2, 4, 7, 8, 11, 13, and 14, and so it has 1, 2, 3, 4, 5, 6, 7, 8 elements. And U of 7 has 6 elements. U of 12 we can work out the same way. We can write down the residue classes mod 12. And now 12 is divisible by 2 and 3, so we need to cross off any residue class which has a factor of 2 or a factor of 3. So 0, 2, 3, 4 is divisible by 2, 6 is divisible by both 2 and 3. 8 is divisible by 2, and 9 is divisible by 3, and 10 is divisible by 2. So we're just left with 4 things: 1, 5, 7, and 11. And so U of 12 has 4 elements. And finally, U of 30. So I won't write down all 30 residue classes, but instead, let's just see if we can figure out what they are using the fact that we have to strike out anything which has a factor in common with 30. So anything which is divisible by 2, 3, or 5. And if we just write down odd numbers, we've taken care of 2. So we're going to write down the odd numbers, and we're going to strike out the ones which are divisible by 3 or 5. So 1's okay, 3 is divisible by 3, 5 is divisible by 5, 7's okay, 9 is divisible by 3, 11's okay, 13's okay, 15 is divisible by both 3 and 5, 17 is okay, 19 is okay, 21 is divisible by 3, 23 is good, 25 is divisible by 5, 27 is divisible by 3, and then there's 29. So if I've done this correctly, we have 1, 2, 3, 4, 5, 6, 7, 8. So again, U of 30 has 8 elements in it. And as you can see, the question of how many elements does U of n have is maybe not completely straightforward. And we're not going to solve that problem now, except we're going to give it a name. And we're going to introduce Euler's function phi, which is by definition, phi of n is the number of elements in U of n. So phi of 7 is 6, phi of 15 is 8, phi of 12 is 4, and phi of 30 is 8. And the one case which is maybe easy to see is that if p is prime, then phi of p is always p minus 1, because u of p just consists of the residue classes 1, 2, and so forth up to p minus 1, because none of those factors can have a factor, none of those numbers can have a factor in common with p if p is prime. So 0 has a factor in common with p, but none of the other residue classes do, and this shows us that u of p has p minus 1 elements. And now let's apply Lagrange's theorem to u of p. And this is usually stated as Fermat's little theorem. And it says that if p is a prime number and a is an integer not divisible by p, then a to the p minus 1 is congruent to 1 mod p. And so what's the proof here? So let's use, first of all, the fact that u of p has p minus 1 elements. And let's take our a, which is an integer not divisible by p. And that means that the congruence class of a is an element of u of p. And back in our discussion of cyclic groups, we proved that the order of an element, we proved the following result. We proved that a to the k, I mean, this is applying it to this particular situation, is equal to the identity if and only if the order of a divides k. And remember what the order of a is. The order of a is the number of elements in the cyclic subgroup generated by the residue class of a. And this is a subgroup of u of p. And u of p has p minus 1 elements. So by Lagrange's theorem, the number of elements in the cyclic subgroup generated by a, which is a subgroup of u of p, has to divide p minus 1. In other words, the order of a divides p minus 1. But by this result, which we proved in our discussion of cyclic groups, if the order of a divides p minus 1, then a to the p minus 1 has to be 1 in the group. And this is just a fancy way of writing that a to the p minus 1 is congruent to 1 mod p. And so we proved Fermat's little theorem. And we could check this in a few special cases. If we go back, let's look at u of 7. If we take 2, our a is 2, then 2 to the 6th well, it's actually equal to 64. It's 4 times 4 times 4. And that is, in fact, congruent to 1 mod 7. And 3 to the 6th is, well, there's various ways of computing this. It's 3 times 3 times 3. Sorry, 9 times 9 times 9. Or 81 times 9 mod 7. Now, 81 is 77 plus 4, so it's congruent to 4 mod 7. So 81 times 9 is congruent to 4 times 9, which is congruent to 36 mod 7. But 36 is congruent to 1 mod 7, because 35 is a multiple of 7. And if you're still skeptical, you can do a few more examples and see that this always works out. And now we can state Euler's theorem, the proof of which is almost exactly the same, but it's for the case where n is a composite integer, and a is an integer which has no factor in common with n. And under those hypotheses, the Euler's theorem says that a to the phi of n is always congruent to 1 mod n. And the proof here is basically the same as the proof of Fermat's little theorem, because what we do is we take a, the residue class of a in u of n, since the GCD of A and N is 1. That's one of the hypotheses. And that's what it means to say that the residue class of A is an element of this group U of N. And so therefore the order of A divides the order of U of N by the same method that we used before, which by definition means that the order of A divides phi of n. In other words, A to the phi of n is 1 in U of n. And that's the same thing as saying that A to the phi of n is congruent to 1 mod n. So if we go back to our earlier examples, let's look at phi of 12 was 4. So remember what U of 12 was. U of 12 consisted of the elements 1, 5, 7, and 11. And phi of 12 was 4. So what is 5 to the 4th? Well, it's 25 squared. But 25 is already congruent to 1 mod 12. So it's also true that 5 to the 4th is congruent to 1 mod 12, because actually 5 squared is already 1 mod 12. Similarly, 7 squared is 1 mod 12. It's 49, because 49 is congruent to 1 mod 12. And so therefore also 7 to the 4th is congruent to 1. Because if you take 1 and square it, you still have 1. And lastly, 11 squared is 121, which is 1 more than 120. So it's congruent to 1 mod 12. So 11 to the 4th is also congruent to 1 mod 12. So in these simple examples, we see that Euler's theorem holds. But the thing to remember about both of these theorems is that they are applications of Lagrange's theorem together with what we know about cyclic groups or order of an element to the special case of the group U of n.